Hello, everyone. Am I streaming to two places? I'm just going to take some time and get going here. Looks like I might be streaming to YouTube twice. The restream stuff changed a little bit. Yeah. Oops. I'm going to turn one of these off. Boop. Okay. There we go. Hi, Tyeth. How's it look on your end? YouTube manual is what went to my pre-existing thing. I don't see any way of pausing. How do I pause? Pause. There. All right. Hello, Raul. Raul? Congratulations on the baby/babies. Yes, we had our second child. I guess I'll do the intro and I'll cover that. Let me first hide this. Hopefully you can hear me. I got restream going in two places. Well, I turned one off. All right. Got my Windows set up. I'm a little rusty. So, hello everybody. It is 2 o'clock on a Friday in December here. My name is Scott. I work on CircuitPython for Adafruit. Adafruit is an open source hardware and software company based out of New York City. You want to support them and support me, you can go to adafruit.com and purchase hardware there. Let's see, what example hardware do I have here? This is a feather format board. So Adafruit makes little devices like this. This has a screen. You can plug in the USB, and with CircuitPython, it shows up as a CircuitPy drive, and it has a code.py file on it that you edit, save, and it just runs. It's super quick, super easy to get into microcontrollers. So CircuitPython is a version of the Python language for microcontrollers like the one I just showed you, which is an ESP32S2. It has Wi-Fi support and native USB, which is pretty cool. So yeah, deep dives are a thing I started during the pandemic, and I've mostly kept them going, although I have been taking some time off because I see the wrong title here, but I might be looking at the wrong chat. I don't know. It looks right now. Yeah, so I've been doing deep dives pretty regularly on Fridays, except when I'm on paternity leave, because I've had now 2 children while doing deep dives. So a huge thank you to Tim, Foamy Guy, who goes by Foamy Guy online, who fills in for me on deep dives when I'm not able to do it. So this is a typically 2-hour stream where I just cover what I've been working on in the past week. We'll see how my brain does. I am definitely sleep deprived because I have a one-month-old at home that likes to wake up in the middle of the night and needs diaper changes and things. But I've been doing some interesting stuff. So I came back. My plan is to take, so my daughter was born on the 29th of October, and she's healthy and growing. She hit her due date, so it was kind of all routine stuff, which is good. My wife is recovering, so everyone's good. It's just typical newborn stuff. Hello, Beata, and hi, DCD as well. So yeah, I came back last week. Last week was also a holiday week with Thanksgiving. So I did the first 3 days, and we were chatting in an internal meeting. So what I was doing before my leave was working on CircuitMatter, which is an implementation in Python of the Matter IoT spec. As I was gone, Dan picked up that work and has been refactoring it to make the cryptography stuff better isolated so that he can move it to CircuitPython. So Dan's working on the task of getting CircuitMatter on CircuitPython. It kind of left me to like maybe not jump into that. The thing that I did pick up is I had gotten support. So the ESP32P4, this is a giant screen. And on the back is the newest super fast chip from Espressif. This is like a test chip of it. It's not really in production yet, but it's like 2 RISC-V cores that are like 300 megahertz or so. I had gotten CircuitPython working on it, and what I picked up is TinyUSB added support while I was out, so I was like, I'm just going to get USB working on it, because I had skipped it before. So I did that. Thank you, HimsLabs, who says congratulations. Oh, I should say also, like, this middle chat is the Discord server. If you want to join that and chat anytime, you can go to the URL adafru.it/discord to join the Discord chat. Hi, Spaceman Spiff. Happy Friday, all. You too. So when I came back, I did the ESP32P4 stuff, and then I was talking about the fact that I'm going to be out a lot next year as well. So I'm taking 12 weeks total of paternity leave, and we're going to try to stretch it so that we don't need a nanny before Rin, my daughter, goes to daycare after she turns a year. And my plan is but the tentative plan is, well, I'm taking 12 weeks total. I already took 4. So when my wife goes back to work, I'll take 8 off completely. Last time I did 6 and 6. This time I'm doing 4 and 8. So I'm going to be out like 2 months of next year. And then after that, depending on childcare, I may actually be part-time for a while because I'll be watching her and working at the same time. So I was kind of like, setting those expectations and kind of thinking about what we can do in the 4 or 5 months that I'm here before I take those 8 weeks. Lamore said, well, is there a way that we could make CircuitPython easier to port to new chipsets? Because it's kind of a big lift to add like a new chip family. And that got me thinking, because there's this project called Zephyr, which is an open source. Let me just pull up the page. Zephyr is not the first result if you type in Zephyr. Let me show my desktop. If I do Zephyr RTOS. So this is the Zephyr website. I don't know why this flag is so tiny, or this kite. So Zephyr is this real-time operating system. So this is a real-time operating system does low-level like thread management and locking and things like that. And then Zephyr is kind of a much bigger project because it includes things like a Bluetooth stack and a network, or like a Wi-Fi networking stack, and a whole lot of other stuff, sensor devices and all this stuff. For a while, I actually was a member of the technical steering committee because for a while, Adafruit was paying to be a Zephyr Foundation member. And when you pay for that, you get a seat in the steering committee. So I've like lurked on the Zephyr project for a long, long time. And one of the main reasons it's been on our radar is that Nordic, creator of like the NRF 52840 and some newer chips that are starting to become available, they've kind of gone all in on Zephyr. So they're one of the major players developing Zephyr. And so if we want to support new Nordic chips, we kind of have to come up with a plan. And we were talking about this NRF54H20, which is, I don't know why key features is collapsed. It's multiple Cortex M33s, clocked up to 320 megahertz. There's a couple RISC-V coprocessors as well, a mega of RAM, which is awesome, high-speed USB. Some really interesting stuff, like thinking about the future of CircuitPython. If we look at the ESP32P4 as well, you'll see it's kind of in the similar vein. So it's a dual core RISC-V. Up to 400 megahertz a piece. This also has high-speed USB, 2D DMA, and a lot of other stuff. MIPI, DSI, and CSI, which are camera and display interfaces. So these chips kind of like feel like the future of CircuitPython. And so thinking about these two chips and thinking about this, like, hey, how do we make it easier to bring CircuitPython to new platforms? Kind of led me to this, like, maybe it's time that we do Zephyr. The other thing that's in my brain about this is that Jeff, Dan, and I have really said, like, at some point we're going to want an RTOS. Because we do this like background task management of like display IO, pixel computation, and synth IO audio computation. And like to really do that well, we need an actual RTOS, especially for these sorts of chips where we have multiple cores. So Hams Labs asks, how does Zephyr compare to FreeRTOS? So FreeRTOS was the thing that I was kind of assuming we would do. FreeRTOS is kind of, when I said what Zephyr was, like about the kernel and the synchronization and threads and stuff, like Zephyr or FreeRTOS does that, but it doesn't do a whole lot more. We actually run CircuitPython on top of FreeRTOS already for all of the expressive chips because the ESP IDF is based on FreeRTOS. So that, and because of that, I have some experience. I'm more comfortable with it. But that doesn't really solve all of the things that we're talking about, right? So the other thing we're thinking about is these Nordic chips. So FreeRTOS is different from Zephyr in that it doesn't really have a hardware abstraction layer. Or a Bluetooth stack or anything else. The Bluetooth stack that the ESP IDF uses is called Nimble. And Nimble actually originates in another open RTOS called mynewt that is really not kind of... It really hasn't gotten adoption like Zephyr has. You can see like the latest release was 14 months ago, according to Wikipedia. And frankly, like it's just not being developed that much. It doesn't seem to have the momentum that Zephyr has behind it. You can see these supported boards here, and it's like, I don't know, 30? I guess I could count. But if we, I thought I had it open. Basically, like, everybody settled on Zephyr. Like, all of the major vendors have settled on Zephyr, and that includes, like, I was chatting with somebody who works at Espressif, and they pointed out that Espressif is now officially supporting Zephyr as well. Which DCD had asked, I saw some news about Zephyr and Arduino. Did this affect your choice? I had seen it. They had announced it when they first announced that Embed wasn't happening. They had announced that they were going to do Zephyr with Arduino. So it kind of like it did just like add another +1 to this idea. This +1 to the idea that like Zephyr is really where folks are going. The Zephyr project is administered. It's under the Linux Foundation, and it is like super open, liberally licensed. So it's just got a ton of momentum. Actually, we could GitHub it. Apache, mynewt, nimble. It's not even listed as a popular repository. Like, okay, mynewt core has 800 stars if we're using stars, and we can look at insights. In the last week, they've had 5 active pull requests. And then if we pull up Zephyr and we do the same thing, it's got 11,000 stars. And if we look at insights, they have 425 active ones in the last week. So like, yeah. Hamzab says, by any chance is mynewt tan? It might be, although maybe that was its downfall. Zephyr being a new choice for single board computers back in the Qualcomm Dragon Board days. Yeah, I think they do have the ability to run on Cortex-A level stuff. But basically, like, this is where the momentum is in terms of the open source RTOS space. And then on top of that, the Zephyr project has a lot of APIs for other things like I2C drivers and I2C drivers and SPI drivers and devices on top of that. My gripe with Zephyr for a long time, because I've followed the project, like I've watched it a lot, is that it's a lot of people in the project have experience with Linux. It's administered by the Linux Foundation, so that's not surprising. But it means that they kind of model a lot of what they do based on how Linux works, which is fine if you're comfortable with how Linux works. But if you're not, like I'm not, it can be a really difficult thing to get into. They use things like devicetree and kconfig for configuration stuff. And they also have the problem that a lot of vendor SDKs do, where they assume a lot of decisions are made at compile time. They're not made at runtime, which CircuitPython and MicroPython want to make as many choices as they can at runtime. Let me just show you. I was looking. So MicroPython has Zephyr support. They have a port that targets Zephyr, but they also have all their other ports. Now, if we look into Zephyr and machine I2C, here's their making the new object. So this is where in CircuitPython we would figure out if the pins you gave us fit for anything, and then we'll start it up. But you'll notice there's these errors that say explicit choice of SCL and SDA is not implemented. You can't choose the frequency and you can't choose the timeout. So basically it only works if you've decided all of it beforehand. So it's pretty limited, and the MicroPython Zephyr port is kind of fixed into it. I want to go a little bit crazier. One thing that we've done pretty successfully, I think, in CircuitPython is really take things and just apply it across the board. So my intention with the Zephyr work is to actually apply it across the board. Basically move all of the boards that we currently support over to Zephyr. That is a big project. That's a real big project. So what I'm doing is I'm starting with the Nordic port because I want to support these new Nordic chips. And then potentially, after we have the Nordic port done, we could, in theory, also move or introduce new boards that are supported. Because Zephyr, I don't know how to go to the docs. I'm actually like learning my way around a lot of the Zephyr stuff still. So they have this supported boards and shields page. and they've got 644 supported boards. They actually have more supported than we do. But they have like the Apollos, they have some Arduinos. That's an FPGA. They have a lot of stuff. A lot of supported boards. And in fact, I think they're kind of pumping the brakes on supporting more. But you can see the Espresso stuff is in here. Even some Adafruit boards are in here. So yeah, they have a ton of different supported boards. So in theory, not only am I trying to move the Nordic port over to Zephyr so that we can support the whole range of Nordic boards, but also I want a minimal port so that if you say like, oh, I want to support this board that Zephyr supports, you get like a minimal set, similar to what the MicroPython Zephyr port does. But then for things that want the functionality of dynamic I2C, for example, we'll still have our own kind of port-specific implementations to circumvent the way that Zephyr does it. That's the plan. Any questions? I don't think I addressed... DCD says, I saw there were several learn guides for Zephyr on Adafruit products. Which are you using today? So the board that I'm targeting right now that I have not loaded any code on is the Nordic board for the NRF52840. That's what I'm trying to target. That's what I'm building for, but I haven't actually gotten to the point where I'm loading anything. And then the other thing I should talk about is airlift. So we have this term for external Wi-Fi and Bluetooth coprocessors called airlift. Managing external coprocessors is a huge pain and something that Zephyr is really leaning into, driven by the Nordic folks. So Nordic has a Wi-Fi coprocessor chip. And so Zephyr has a thing called cpbuild that allows you to actually build multiple binaries for different chips on the board and get those all set up. So that's another benefit that I want to get from the Zephyr work, is to manage, to be able to manage multiple chips and cores and architectures all on the same board. Mark says, congrats on the family stuff. Welcome back. I couldn't resist joining when I saw Zephyr in the stream title. Yeah, I think Zephyr has a lot of fans. I've always been pretty wary of it, but I finally, I kind of got myself over the hump of I really just need to ignore the parts I don't want, and take the parts I want to use, the kernel, the BLE, the multi-chip thing, and really lean into it. And then ignore and circumvent for the hardware stuff that doesn't work. We've always felt hung up by the fact that pin configuration and stuff is fixed in Zephyr, but we can write the registers. We can do it ourselves. Hamzab says, I'm excited you'll have RTOS supported on your boards. It'll make things a lot easier for me. Yeah, I think as a consequence, we'll probably get board definitions, Zephyr board defs for all of the Adafruit boards. Probably all the boards that CircuitPython supports. So in theory, you could actually just write Zephyr based on those board defs too. Taya says, so you intend eventually for things that are currently compile time decisions to be allowed to change at runtime in Zephyr, like the I2C pin speeds and BLE services. I'm hoping BLE services can be dynamic in Zephyr right now. I should double check that. I looked at MDNS and MDNS is not. So my plan is that basic basic boards that don't have any special support will just be fixed, right? They'll be within the constraints of what the Zephyr API can give us. But then for boards that we already, or ports that we've already done, we'll just reuse all of the common HAL stuff still. So you'll still do I2C outside of Zephyr. You'll do I2C using our implementation that targets the vendor hardware abstraction layer. So Zephyr still uses what's called NRFX under the hood, And that's what we use in Common HAL in most places too. So like we'll migrate Common HAL stuff over to the underlying. We'll go around Zephyr if we need to. Fede2 says, will this enable OTA updates to CircuitPython? That's a good question. And that's more of a question about bootloaders. So there probably is a world where we have basically like board variants that assume that you have an OTA capable bootloader. But that's a pretty big change. Because we like our UF2 bootloader that doesn't do OTA. So potentially, yeah. OTA updates, which OTA is over the air, or kind of like automated. Yeah, Yanni says having the base stuff and then specific stuff. Yeah, so we'll treat it in a lot of ways like we do normal vendor SDKs. We'll take the parts that we like, build on those, and then we'll go around it where we need to. That's the theory. That's my theory, and that's what I'm working to prove out. But I'm not there yet. So where am I? Where did I start? So if you've watched Deep Dive before, you know I have a bugbear about our build system. And if we want this world where we kind of start with Zephyr and go from there, is we need to start with the Zephyr build system. Instead of, right now we have kind of like make files on top of vendor SDKs or even around circumventing vendor SDKs. My approach so far has been to take the vendor build system and I discovered so the vendor build system, or the build system in Zephyr is called CMake. They use a project called CMake, and they have this wrapper called West, which is a command line program to run it. They have a lot of tools and a lot of configuration files and stuff. But what I've decided to do on the build side, so to get one of the hard parts about setting up a new port with CircuitPython is having the build system set up. It's a mix of like setting your own makefile upright and then also reusing some shared makefiles that cover like the circuit or the MicroPython core, and then all the configuration stuff. And those of you who watch Deep Dive may know where this is going, because I figured out how to have the Zephyr CMake file call a Python script that builds all of the CircuitPython stuff for me, puts it in a .a, which is like just a wrapper around .o files, and then links it to Zephyr. And that Python file does not use make. It actually is an async. It uses async IO to build everything. TCD says, we've done some work to extricate CMake from our RP2040 builds while still using the RP2040 SDK. What are you using instead? If you're getting rid of CMake. So I'm working within the bounds of CMake. I'm having CMake call out to me. And I figured out how to get CMake to tell me like, hey, what compiler are you using? So all of the like, make sure the tool chain's set up right and getting the compilation flag set for a particular target is still handled by Zephyr. It just like passes those all to my Python file, and then my Python file uses them. So what does that look like? Well, let's start by, I will clear my screen. Let me get this full. And I'm gonna, so right now it just builds into a build directory, which is not exactly what I want. But what I have here is, and is that too small? It might be too small. I'm clearing the terminal, and then I'm timing West, so that's Zephyr, build, -B for board, PCA 156 is what we call the Nordic NRF 52840 board. They actually call it something else in Zephyr, and I have an alias between the two. I'm asking it to do Unix make files, and I'm asking it to do it in parallel for 32. DCD says, we found it hard to understand what CMake is doing and try to build a flatter project directory in Make and other scripting languages. Okay, so I've removed, this is a clean build. So there's West. And now we'll get to Make, building Zephyr. And this is a debug output of it's debug output of my Python project building stuff. And we can see here we're getting errors. And those are interesting errors. I haven't looked at those before. Because it's asking me about sysheap when I was doing kheap, which is interesting. I don't know a lot of Zephyr. Hi, Jonathan. I see you're typing. I don't know which heap to use. That's where I'm at. So that took 10 seconds. Now let's see what happens if I run it again. And I didn't delete the build directory. I just cleared the terminal. It's nice clearing the terminal because then I can get right to the top of my output. So now it took 7 seconds, which is actually slower than I thought it should be. But I'm also printing a lot. But it should have not. It still compiled a lot. Interesting. Pre-processed some. It might have been just like some stuff didn't fully finish. David says, while this is interesting, I just used CircuitPython to control boards from Adafruit and boards I designed to make a specific product for my own use. Will this impact the simplicity of CircuitPython? My goal is no. My goal is to have the same experience with CircuitPython, but make it easier to bring it to more boards. So I still plan on using TinyUSB. So Zephyr has a fledgling USB stack of their own, but I would rather use TinyUSB because we've used it a long time, and TinyUSB is a great project. So we're going to have to figure out how to integrate that. One distinction I've had to round up against already is whether we're going to use the file system stuff in Zephyr, and my plan is to not. So right now I was looking at the block-based APIs for Zephyr. So I want Zephyr to manage Flash, but we're going to use our own stuff on top of that. So the USB mass storage works on blocks. So we'll do tiny USB blocks into Zephyr blocks. And we'll use our own FATFS stuff still too. So the hope is that CircuitPython from the outside won't change. It'll just work better. Knock on wood. But it'll work better in the sense that like when we have more boards with multiple cores, we'll actually have an RTOS that allows us to like offload stuff onto other cores, which would be really cool. So like if you're doing displayio or audio synth.io stuff, like you may have seen that like it slows stuff down. Whereas like we could like offload that to another core and keep your Python running faster. Jonathan Berry, who is a Zephyr advocate, says it's possible to develop Zephyr without West, but still using CMake. You're better off using West. Yeah, I don't. I'd rather get rid of CMake than West. But Jamie is my guess. Does this potentially mean Zephyr drivers for Adafruit breakout boards, sensors, and displays and stuff? That would be incredible news. ZMK got me hooked on Zephyr. I would say, unfortunately, that's not my plan. We don't plan on using that stuff. Like, we'll still have Python level drivers for that stuff. We're not planning on doing Zephyr drivers for that sort of thing. Because Zephyr is not very dynamic, and we want it to be a lot more dynamic. So no, the answer is no. We don't really plan on taking advantage of the sensor stuff. I think the one exception to that rule is that like if there's some I2C chip that's like helping a board do something like power management, like then we would probably anything that's on the board is pretty fixed. That might be a case for like actually having Zephyr manage it. But generally, no. Generally, our drivers will still be in Python, and that's also makes sense from the standpoint that like we also use Python drivers on single board computers via the Blinka stuff. So I don't think it makes sense for us to put a lot of effort into drivers at the Zephyr level. It does mean that like microcontroller boards will have board defs, but it doesn't mean that like breakout boards will. Yeah, good question. While I'm talking about crazy ideas, the other crazy idea I had about the future is the future of CircuitPython is with these new devices, they have a lot of RAM and they're really fast, and displayio is really slow. Displayio is deliberately slow so that it can fit into little bits of memory. And I was thinking, kind of in the back of my brain, I want to have a second implementation of displayio that isn't concerned about memory. It's more about performance. And my brain just kind of clicked and said, you know what? I should implement displayio on top of lvgl in CircuitPython. So that's kind of where my brain settled with that. I haven't started that work at all, but that's kind of where my brain is like, okay, like when we want to redo displayio, we'll do it on top of lvgl under the hood as well. Because lvgl has some like, it uses some accelerators on boards already. And then in theory, we could like add a second API that would also interface with lvgl stuff. But the MicroPython port is not officially MicroPython. It's somebody else maintaining it. And their API is not very Pythonic. It is literally like C for C, or like Python function for C for every C function. First, I'll do the internal stuff, and then maybe we'll figure out what to expose. But I am not working on that, and probably not anytime soon. So don't get your hopes up. The Zephyr stuff comes before that. So that run took 5 seconds, and most of it's this west timing. So this is interesting. So it got down to 4 seconds. So how is this working? This is most of what I've done. I actually get it to the link phase, but and if Jonathan's still watching, should I be using sysheap? This is the first like actual Zephyr I've started doing. It's mostly been getting to the point where I've got like something that links that doesn't have everything it needs. So yeah, what heap do I use? How do I allocate stuff? But yeah, it seems that I have the build system integration happening. So how does the build work? Well, it's now at the top level. So if you've done a CircuitPython board build before, you know it's usually in CircuitPython ports and then the vendor, and then that's where you do a build for a particular thing. But my goal with the Zephyr port is to factor that out. So now it's at the top level of CircuitPython using West. So at the top level, we now have a CMakeLists that is Zephyr. And we say our project CircuitPython. We have this Zephyr main target. Some nice says LVGL looks neat. I had not seen that. Yeah, people are excited about it. K-heap? I'm confused between K-heap and whatever it's trying to tell me I should use. Sysheap? Or there's also a multi-heap thing. There was like 3 different types of heaps, and I wasn't sure which one to use. So how does it work? Well, we say, oh, our source is Zephyr main, and it turns out Zephyr main is empty. Or no, I say we use a unique name for CircuitPython. So we just have main that calls CircuitPython main, and then in our main, we just say, hey, if we're Zephyr, we're actually called this other thing. Because it turns out there's a weak main in Zephyr that if you have the weak main, it doesn't actually include the main from this lib.circuitpython.a that I'm building. Okay, so I just use kheap. All right. All figured out. I'm just getting to the Zephyr part of things because I've been distracted with build system stuff. But I'm pretty happy with the build system. So CMakeLists get some information. So like, what are the includes? What are the definitions, the options? I don't know why I have this. External project C flags. Oh, this is just like getting the compiler out of it. I don't know. But then we do this external project add thing. So this is how you get CMake to call some other build system. And it can even like download and configure and install things. But I'm having it run Python tools cpbuild build CircuitPython. And I'm giving it a bunch of arguments, like what compiler to use, what C flags to use, what the board is, the board alias. So the board here is the Zephyr name. Board alias is what you put in on the command line. They also have revisions and qualifiers, information about the system on a chip, and then where to put it. So we're going to put it in libcircuitpython.a. We are job server aware, and we always build. So this means that CMake runs it every time, and job server is the way that make conveys to subprocesses how parallel they can be. So I did the -J32, and like make will use some of that parallelism and then also allow the like subjob to use some of it as well. I'll show you how that works. And then you wrap it, and that's it. So that's how you get CMake to call your thing. What does our thing look like? So if we go in Tools, Build CircuitPython, well, first we say hello, and we just print everything out. We capture source directory and build directory, obviously hard-coded to my path right now. We take in the CMake args, and we parse them a little bit into dictionary. We hand those to this compiler, which is like a higher level thing to call the compile thing. And then some settings here that I'm starting to play around with. Now let's go. So this script is 336 lines long. So we do async IO run. So that's how we get parallelism is we're using Python's async IO can call a subprocess asynchronously. So we basically have one task that's running this Python stuff, and then the remaining tasks are running other things. And that actually makes me think about that I'm using one extra. I'm not using one extra. I think I don't know. Maybe I'm using one extra. I'm setting a log handler. I'm doing async IO run main. Main just awaits build CircuitPython and then captures any runtime errors and hides them. So this is runtime error is raised if compilation step fails. So by capturing it, we just we do sysexit so that make that was generated by CMake knows that we failed. But we don't print the like stack trace for that sort of failure. If your Python has errors that cause some other exception, then you'll get the backtrace for your Python code. Okay, so build CircuitPython is the next thing here. So we're going to set some flags. And this is actually taken from my earlier attempt at making a Python build system for CircuitPython. So I've done some tweaks. But I'm like, that's the origins of this stuff. So doing some flags. So here's some flags that we need. The first thing that we do, so we have the cpbuild run command, and it calls Python the make version header file. And I actually had to touch it. So it's interesting, and this is one of my gripes about the build world right now, is like all build systems, like even Zephyr, they have like multiple phases of Python files that they run during their build system. And it's just crazy to me that like it should just be all Python. And furthermore, our like make version header, if we look at this, to make, so the version header is included in a lot of things. And if you change it every time you call this, you're going to rebuild a bunch of stuff that you don't actually need to rebuild, because make itself is only looking at like the time that the file was changed. Even if it was not changed, and like even if the contents didn't change, it just does it based on time. And because of that, we have this thing. So if we look at make version header, we compute it, and then we say, oh, like we actually check, we read the existing version of the file, and if it's the same, we don't actually write it out again, which means that you don't trigger this like downstream build. But I'm doing something slightly different with the cpbuild stuff, where I actually make sure that, so run command doesn't know which files are inputs and which files are outputs. It only knows that there are some files related, and it keeps a separate time of when it was last run. But it also is checking to make sure that one of those files that's on the command line changed time. So I actually have to circumvent it by touching the file to make sure that the time is newer. And I've added this to this run command. I can say, hey, check the hash of this version header, which says, this is the same check. This is say, hash the file beforehand and then hash it after the command is run. And if it's the same, set the time back. But it still knows that this command was run later. Am I losing people or what? So now we do some source files. We add some more files that we want to compile just based on a glob. And then np config board, since we're not using make anymore, becomes a .toml file. And this gives us USB information, for example. I should also point out that I moved boards to the top level. So this is all of the NRF boards now are in the top level boards file, not in ports Nordic. So my goal is that if I can move the Nordic port and have this stuff alongside the existing system, we can build Nordic with Zephyr, but the other ports just work as is. So I can be pretty aggressive in changing the Nordic stuff, but I have to be very careful anything outside of that. So now I'm using the directory names and share bindings to set my CircuitPy flags. And I just set them all to 0 right now. Nothing is on. There's some np config flags that we have to do too. And we set those to 0 as well. We have some source files. We glob everything in the Py directory. So that's like all of the VM stuff. And now we do the QString generation. So this is one of the, one of the pains. Actually, let me show you this. So async task group, this is a way of doing multiple tasks at once. And so I'm creating a new task to pre-process and split the definitions for every source file that I've kind of like gathered in this list. If we look at the way that we do it in the actual file, it's using multi-processing. So instead of relying on the make build system to do multi-processing for this QString stuff, it actually is doing it itself. So this is another case of our Python scripts doing stuff that I think like a better build system would do. So we still use this script, but we only use it for a single file, not a bunch of them, I think. I forget. And this file does like different things, like splits or concatenates. So yeah, so this is doing, basically, you pre-process the file, and then you like regex it, basically. So if we go up to pre-process and split defs, we say, okay, we're going to create this pp file, and we do it for queuestrings, modules, and root pointers. So we do it 3 times. Well, we pre-process it once, and then we use makequeuestrdefs to split it out in 3 different modes. And actually, we can do that asynchronously. So here's another. So task group is a way to do things asynchronously, and if any one of them fails, the rest of them get cleaned up. So we pre-process and split defs. And can I go back? So we do that for all the source files, and then we generate queue-string headers. We also generate module headers, and we do root pointer headers. So this is like those 3 modes, but we're doing like more stuff there. So if we look at, so generate root pointers, we collect all of the root pointers together, and then we call this make root pointers file. If we collect all the modules together, and we do make module defs, and if we're doing queuestrings, then we snag queuestring defs out of pi. So these are like fixed ones. We do some sed thing and then spread it out. We pre-process that file. We run something else with it, and then we also collect defs. And then we do translation stuff and make translation data as well. And we could parallelize some of this. So one thing that's interesting is this isn't like in make or cmake or in make or cmake, like the way that the order that things are done in is implicit, not explicit, right? So you in make or cmake, you say here's an output, here's its dependencies, and here's the command to convert these inputs to output, inputs to the output, and then the system magically figures out what order to do everything in. And in this way I'm doing it here, that's explicitly not what's happening. It's Python, it's in a particular order. So your dependencies of like what runs when is actually dependent on this. Like it's dependent on the code. It's explicit, not implicit, which is why we're talking about queue-string generation. It's implicit in our make files that like all of our compile steps depend on some header that gets generated, right? Like comes queue-string generated header, where here it's very explicit. DCD says, this is great. What are the root pointers? Root pointers are pointers that are meant to be GC roots. So they're pointers that live outside of the main heap, but point into the heap, and you want to keep them alive when you're doing garbage collection, if that makes any sense. So collect defs is a shared command, and it's just, I actually switched it from make queuestrdefs cat to actually cat command, and -s. -s just strips repeated blank lines to make the output file smaller. And I'm actually doing the glob here. So this is going to enumerate all of the files within the directory where the split versions of those things went. So they're not related to queue-string. Root pointers are not related to queue-strings, but they're related to like things that are registered, right? So like you put some special macro in the source file, like I want to add this module, or I want this root pointer, and then like both for those things and for queue-strings, you need to pre-process first, so that like if you're not doing a particular module, its root pointer or its module definition just goes away when you pre-process it. And that's true for queue-strings as well. So there's like this shared pre-processing step. Then there's a split thing that like regexes across these things to split them into different files, and then they get concatenated together, and then they get parsed, or like different headers are generated for the different things. This is not new. Like, this is the way the makefile and the CMake builds work as well. It's just like complicated. And that's all like, that's not build system-y stuff. That's just like micropython isms. Okay, how far did we get down? So we've generated our headers. And now what we're going to do is I have this ever-growing list of things that don't need to go through that process. So I add more to the source files, including this translations.c, which was generated by that step. DCD says, I see that we definitely need to do this outside the CMake process. Makes sense. Except for the fact that MicroPython currently maintains both a CMake build and a make build that does both of these things. So you can do it by having like everything that we're just about to do depend on an output from that queuestring process. So it just makes a lot more sense to me done this way, where you're reading code and you're like, okay, we're going to do queuestring generation and then we're going to do compilation. So, all right, now what we're doing is we're saying for every source file, we're going to like do some path stuff. So this makes heavy use of Python's pathlib. That's how it knows when you call run command, it expects pathlib path objects for any path that it needs to pay attention to. If you use just a string, it won't know its path. But now we're doing another task group, and we're just going to compile everything at the same time. So we just create a task for a compile source file, the object file, with our flags and port flags. Port flags is empty. The flags that we got from Zephyr are part of this compiler object. So we don't need to worry about passing them around. And then we call archive, which takes all the .os and puts them in an A. And that A is what Zephyr CMake links to. Any questions about, so this is the file that builds very minimal, doesn't actually work yet, CircuitPython. It's not handling any of the, like, for this board, I want to turn this module or that module on and off. Well, I'll have to decide how to do that. So it doesn't fully replace like npconfig port and npconfig board.mk, the .mk version. The .h's should be fine, but the MKs are the ones that we're going to replace. So what does that look like? Well, let me show you something cool that I've added. And let's actually delete the build directory again. And let's run our build. We'll see how far it gets. So there's make building stuff, and now this is my script building stuff. And we've crashed, and it says, hey, look, I wrote a trace. So I don't know if I showed this last time, but this is something I added in my like previous iteration. But if we pull up in here, we go build, CircuitPython, source, build, and then trace goes in here. You can see here's our last build times file. So this is what tracks for every run command that's called, it makes a hash. And then that hash is stored in a dictionary along with the like timestamp of the last time it was run. Instead of the way that Make and CMake do that, I think, is that they look at the output file's timestamp. I think, maybe not. But now there's a trace.json, and you can see I do have one loaded here, but I'm going to load this newer one, and we'll see what we see. So this is pretty neat. So this is showing for 31 threads. What is it doing? So this is how long the MP version header takes. So we have to do header version first before we do all the pre-processing. And then this has the names of the thing that showed up in the thing, and it tells you how long it did. And it tells you kind of like what CPU ran it. It's faked. It doesn't know what like the CPU number. It just knows that like Yeah. So, and then, so this is all the like parallelism of pre-processing all those files and then splitting them. You can see here, like this is splitting obj range into Q strings. And now there's this like, okay, now we're going to do the Q string process. And then this is doing the, oh, this is, this longer one is translation generation. And then this one here is module defs, and then this one must be root pointers. So here we're seeing like a timeline of our build process, and we could say like, oh, like, however, like half a second, 532 milliseconds is spent doing compression of translations. That's what this is. Which is interesting because we don't actually need to do that in order to compile most things. So like, I also like this idea of using async Python because it helps us to reorganize things. And that, like, somebody would argue like, oh, like that is a benefit of something like Make, where it like should automatically determine that, but that's if you get the dependencies right. And that's really hard to get the dependencies right. Okay, so the rest of this stuff is just doing compiles in parallel. And then it crashes, so yeah, it didn't get to the point where it was doing the link phase. Okay, so that's cool. Do people want to see cpbuild? I want to show cpbuild, but it's where I spent most of my time this week because I got it doing parallelism interfacing with CMake. I got it detecting when not to run a step again. So actually, let's just see what a trace looks like if we do it again. So we'll run it again, and we'll look at the trace again. So it was 292 K here, and now it's only 85. So we did less work. So if we decide not to run a step, it doesn't show up in the trace, which we could actually include the Python trace stuff. But so did we do some pre-processing still? Looks like we did. Compile, 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 compile. There's one pre-process. I wonder why we redid pre-processing. We shouldn't have. I think what can happen is that, no, my code doesn't work perfectly. Yeah, so the visualizer here is called Perfetto, like you're talking about. I don't know why. I wonder if my file didn't get written. Unfortunately, my clear doesn't like help me. Now if I do this one, should be quicker. Yeah, it took 5 seconds, and it's only 27K. It's still showing pre-process phase. Although it didn't run everything again. Huh. I'm not entirely sure why it's running the pre-process phase still. It should know that the files haven't changed. Although I think I do have a problem where if whatever is happening while something fails, we don't remember that the other stuff worked okay. Okay, so it's Friday. I mean, I should try to fix this. Yeah, maybe we... Chad says, I just joined what's Zephyr. Zephyr is an open source real-time operating system So it manages hardware, and it has a kernel that does threading and manages memory for you, things like that. So it's got a very standard layer across different microcontroller vendors and stuff. Is that a good... I'm new to the Zephyr world. Is that a... Well, I'm new to explaining what Zephyr is, so that might not be a great explanation. I wonder why that is happening. I think I want just kalec. K-free. K-realec. Like, I don't know the basics. Zephyr API docs. I don't want multi-heap. I want heap management. Shared multi-heap. This is why I'm like... It's complicated. K-heap init, that's the synchronized heap allocator. The low-level one is kmalec. Okay, so I do want the k-heap variance. Here we go. Include Zephyr kernel. Let's do that. Sure. It takes initializes a k-heap over a memory region specified by the user. Internal alignment restrictions inside the inner sysheap mean that not all bytes may be usable as allocated memory. I think, why can't I just use the sysheap? I think I just want the sysheap. I don't need 2 heaps, I just need 1. I don't want to init, like, I'd rather just use... Yeah, I don't need multiple heaps. System heap. The system heap cannot be directly referenced using its memory address. Aligned on a multiple of pointer sizes. That's what I want. I think I just want kmalec. I don't want to init. We'll just use system, kalec, kfree, krealec. And we don't give it a pointer. See what it says. if it's gonna... See, that time it didn't do the pre-process again. I wonder why it's redoing the pre-process. So this is as far as I've gotten it, where, oh, that compiled, which is good. But I'm missing port stack get limit. Port init. Port stack get top. Stack init. Okay, so I'm linking, but it's not finding everything. Does CircuitPython do the heap synchronization, or do you want Zephyr to do it? I want Zephyr to do it. I want Zephyr to do it. I don't know. I can't get too hung up on getting exactly the right thing. Like, that's just not going to happen. I'm going to get it wrong. That's okay. But I got this far. So now I need to figure out how, if I'm trying to do, well, port init. Port init's easy enough to add here. I haven't decided if I like the structure, but previous declaration. Oh, it takes safe mode. It returns a safe mode. So I could do port/Zephyr, but I think I'm doing supervisor/Zephyr. I really want to show that, like, this is going to live outside ports. Like, it's blanket. Oh, interesting. Undefined reference to kalloc. Interesting. Maybe these will just stub out, make them go away. Port.h has reset port. The idea being that these are all implemented on top of Zephyr. What else are we looking for? Port stack get limit. I think I might have. I'm going to mess it up, but just wanted to compile. I think I got to figure out how to configure my Zephyr project to get K-free. From the docs, the core port initialization reset methods are defined in CMakeLists port, and they should be first to be implemented. The requirement that they be implemented in the supervisor directory is a build artifact. And I'm breaking it. I like how you're quoting docs that I'm pretty sure I wrote. Okay, we need enable, disable, and reset CPU. I should reorder these. I'm being speedy, although I guess we got 45 minutes. Let's try to figure out this kalloc thing. Oh, it's CMakeLists. That's a problem for that one. Too many arguments, because this one's not synchronized, I think is what it's saying. So my build system is not slowing me down, which is good. Although there's definitely that bug. Control reach is end of non-void function. Port init. Okay. Was it no safe mode? Safe mode none? Guessed. And we don't want this to return. Let's see what it says. So this file is the file that would be, attributes should be specified before the, oh, you know what? I copied it from the header. Is it really going to make me move it? No, it's not really going to make me move it. You know what? I'm going to turn off debug output. In too many files open. Tools, build CircuitPython. At the bottom, like I could add a flag to change that. Oh yeah, and it reran the script but didn't have to build anything. Figured out it didn't need to build anything. Undefined reference to reset port. I thought I did reset port. More, but kfree and CMakeLists are not. So your port is under supervisor Zephyr, but the other files are just under supervisor. I'm playing around with where to put the Zephyr files. I don't really want to do ports Zephyr because in the future, everything is Zephyr by default. Like the port.c will be, there will only be one implementation when I'm done. Right? Like that's kind of why I'm hesitant. I don't really want to make a port Zephyr because I don't want to give the same impression that MicroPython has where it's like, this is something separate. Like, I really want to move everything to Zephyr if we're going to do that. Okay, let's figure out how to run Zephyr menu config, because that's probably what we need to do. Interactive kconfig. GUI config is using West. build your application as usual, and then do GUI config. Does that work? Yes. Oh, it's nice. Okay, I'm not going to do that. I'm going to do menu config because I'm actually more comfortable with it. Okay. Because I know I can hit this and go heap. Device tree info modules. LVGL. Board options, hardware configuration. This is like from the first time I was. Retired Wizard says, so all boards added to CircuitPython will need to be supported by Zephyr also. Not in upstream, but yes, they will need to have Zephyr board definitions. At least in CircuitPython. You don't need them in Zephyr proper, but yeah, like we'll need the files for it. So yeah, there's potentially a lot of work there. But we're already maintaining board information. We might as well maintain it in Zephyr form. And we're going to have additional data on top of that. Like Zephyr doesn't have all the data we want. Let's see. General architecture, SRAM, flash size. General kernel options. Isn't Zephyr becoming your interface to the ports SDK? Yes. Right, like I'm implementing like the ports API right now with Zephyr. But the end goal is to only have that one implementation of it. Because I can't get rid of that stuff yet. Because I don't want to move all the ports at once. That's an even more giant task. Look at memory domains. This is like the first time I look through here, so. I will want dynamic threads. Symbol's currently not selecting the symbol. Is Wi-Fi on the ESP32? Great. That's the other risk is like potentially we'll get like halfway through this and not like Zephyr will not support something that we do on ESP, for example. But Espressif is working on it, so we could go back to them and be like, hey, we really need you to do this. So it could be a long process. But we can benefit from the new stuff can still benefit from it. Store device dependencies, mutable devices. What does that mean? Instantiated in SRAM instead of Flash. Virtual memory support. Console, clock drivers, DMA, Flash, some of these we might be able to use. Memory controller. USB. No, we're going to use our own USB. Floating point and printf. Common implementation of malloc family that uses the kernel heap API. Memory blocks, heap, and memory allocation. Small and big heaps. Some Night says, maybe a silly question. Would Zephyr running with both CircuitPython and Arduino support ever be able to run at the same time on multi-core boards? Maybe. I don't know. Like, I know that Arduino stuff is doing things where it's like dynamically linked into a static Zephyr binary, which is interesting. But I don't know all of the device side of things. So, I don't know. Ah. Multi-heap manager. Okay, so we don't want shared multi-heap. We should be able to just use one. Like ESP Spyram would use it. Why? I don't know. There's a JSON library. Base 64 encoding and decoding. Console subsystem support routines. For dot matrix displays. This is this linkable loadable extensions thing is what Arduino is using, I think. Memory attributes management library. Yeah, like this experimental USB device stack. Build and link features. Orphan section. Link application into the chosen code partition from devicetree. Interesting, you can provide custom linker scripts. Ooh, do we want to bump up to C23? Optimize for size. Color diagnostics. Symbol file, disassembly file. Ooh, we can build a binary in UF2 format. Sorry, this is me just learning. Depending on how Arduino does their threads, it's possible that like maybe we could run on the same core, even. Act as a bootloader. Did it change anything? I don't know where that would be stored. It didn't answer my question. Undefined reference to CMakeLists. Shouldn't that be part of what Zephyr links in? Heap APIs, kheap. I don't want. I just want to use the sysheap. I don't want to statically define my own heap. I just want to use theirs. Like, I want it all. Heap mempool size. Oh, it's 0. I want invites. 32, 7, 6, 8. Configuration saved to build Zephyr config. Where would it? So DCD says, earlier you mentioned creating a .a library. What does nm tell you about the symbol in the library? So the CMakeLists symbol is not one I'm going to provide. It's one that I'm expecting Zephyr to provide. And it actually looks like they are now because we're not seeing it. Like it's finding it now. And if we look, see, it built everything again. It pre-processed it all. I wonder if it's like unzipping everything. Like somewhere in here, or here's k heap. Like maybe that's why it got added. Parsing libzephyr kconfig. Loaded configuration build Zephyr kconfig. Where do kconfigs live? Developing with Zephyr. Getting started. See, they always start with a sample, and I was like, that's not what I want. Building configuration systems. Kconfig. Test out configurations during application development. This page explains how to make settings permanent. Perfect. When making kconfig changes, it's important to understand the difference between visible and invisible symbols. Defined with a prompt. Without a prompt. Setting symbols in configuration files. The initial configuration is produced by merging a def.config file for the board with application settings, usually from prj.conf. Assignments in configuration files use there should be no spaces. I mean, that's good. They're not using SDK config like the IDF does, and it does this weird thing SDK config does where if it's set to no, it like comments it out and says this symbol is not set. Right. A Boolean symbol can also be set to end with a comment formatted like this. This is the format you will see in the merged configuration saved as Zephyr config in the build directory. This is very confusing, and you should not do it. Initial configuration for an application comes from merging configuration settings in three sources: boards, vendor, board def.config, any cmake cache entries prefixed with config underscore, and the application configuration. So we want to move this to the application configuration, but that's not going to work because we want to change it on a per sock basis. We really want it to just be all memory. Why can't it be all memory? Maybe that's why we do it dynamically. But like the sys heap should be there. If conf file is set, the configurations are merged in. Boards revision. Applications can have a sock overlay configuration that is applied to it. The file socks, sock board qualifiers, or comp. After the main project configuration has been applied and before any board overlay configuration files have been applied. That makes sense. Huh. If the symbol is assigned both by the board and in the application's configuration takes precedence. And you can look at zephyr.config for the... Avoid making fixed board-specific settings configurable in interactive configuration. I wonder if we can find the linker script for, we're in build info. This is really handy. Toolchain, SVG. I wonder if we can find, there's a libzephyr.a. Modules. Config. CMake app. Pre0.map. I want to find that. What I'm trying to figure out is if I could dynamically figure out the area that I want. But, I mean, if I'm in multi-threading mode, there should be a heap that it's giving me, but maybe it's all fixed. Zephyr include generated. These are a build.mix. I don't want those. Sysbuild modules. Snippets. Build, Zephyr include generated. Build, Zephyr include generated. App smem. Oh, it's big because there's a comment. Line. RAM sections. ROM start sections. What the heck? What linker script is it using? There was another. There's a way to get it to be more verbose. It's linking the executable, but it's not telling me what it's doing. How did it? Maybe it was without the time that I was doing it. There. Verbose makefile. See if it outputs more. Retired Wizard says, thanks, Scott. It'll be nice having a bit more of an idea what the devs are talking about when Zephyr comes up. Dinner bell is ringing. Have a great night, everyone. Thanks, you too, Retired Wizard. Have a good dinner. Here we go. Here we go. Linker Zephyr pre0.command. Build Zephyr. All right, RAM. ROM region. Text region. Like, this is all of the stuff that app regions I don't want to worry about. All right, this is all Flash stuff. Let's get to the image RAM start. RAM functions, data, kernel, data size, data load start, region start. Sysmem blocks pointer area. Is the heap defined in that command file? That's what I'm thinking. Net buffer pool area, BSS start, BSS end, kernel RAM end is the end of memory. Image RAM end, image RAM size. Kernel RAM and kernel RAM size. Kernel RAM start is before BSS, which is interesting. No init. What was the sysmem section? Yeah, sysmems blocks pointer list. It comes from Flash. Image RAM. Kernel RAM end. Just about to wrap. Well, I guess we got 15 minutes. I should push my work too. MPU regions. Linker scripts, ARM. Kernel RAM start is at BSS start. Linker defs. MPU dynamic regions area size. All unused memory also owned by the kernel for heaps. Right, I want to allocate into there. Cortex M scripts, linker script. This looks relevant. Oh, look, devicetree pre-processing. Great. Heap mempool size, I think, is what I did. I could also look for that. let's just do a quick Cortex A and R. These are all the different linker scripts have these. Oh, somebody sent a message. I've got a Meshtastic radio going. That's the other thing I gotten into. Let's see what we find if we do heap mempool size. Okay, heap define. See, this is where I'm like, what are you doing? You don't need to use, like, this is Python. This would be much better as Python code. Like, don't force me. $256. 16K. The size of the heap memory pool. How do we know? It's fixed? Let's see what this shows. So this says if kheap mempool size is greater than 0. Oh, you know, it's just called system heap. Find system heap. Kheap static system heap. And it's 8,000 long. So when we set that setting, it's just making a static variable to assign it into. Have a good one, DCD. Thanks. Z heap aligned alloc. Thank you, David, for doing time codes. Sent me an email. So only if this is greater than 0 can we do kmalloc. It's interesting, k-free. Thread resource pool system heap. Z thread aligned alloc. If we're in ISR, we use the system heap. Otherwise, we use the current thread's resource pool. K thread system pool assigned. Huh. That's so silly. You don't know how big the image is, so your heap is not large? Everything's fixed until kernel RAM end. All right, well, I'm in the Zephyr weeds. gotten myself there. MPU regions. I mean, I can keep going. I could just set it. Add reserved memory support. Device tree stuff. Any other questions? We're just about out of time. I think the answer right now is just set it. So if we go, we do have a project.conf. We just say, what did I do? What is 64? Yeah, that's what I want. I want 64K. And now let's do a remove the build. Make the build without verbose. Random question. Taya says, ever done an in-memory only app on ESP? Reason you can load into RAM using ESP tool, then say execute. So I plan on having mini firmware app to interrogate the board when troubleshooting for new users. In my head, it sounds good. Sort of a generic version of a serial doctor. I have not. I have not done RAM only ESP stuff. Heap mempool size. Isn't that what it is? It called something else? ChatGPT might have picked the wrong name. Slow the first time. No longer set, but we do the menu config. Heap mem. Heap mempool size. That's what it's called, right? If the sum is greater than the mempool size option, then the actual heap size will be rounded up. Direct dependencies. Kernel mempool. Okay, let's set this to bat. This file, let's see what's in here. Nice. I love kconfig. It's great. Okay, so we probably need this one too. That is going to be my guess. That's the last thing I'm trying. Sysmem blocks. I wonder what that is. I do have to commit this. playing? Yes. Oh, I've got spaces. I bet you that's it. This is why programmers are pedantic. There we go. It was the spaces. I wonder if I need the other one. All right, well, I'm linking against something from my CircuitPython code to that, so that's a start. My build stuff is not perfect. All right, I'm gonna Sublime merge it, commit it, and get out of here. Stage. More work. Okay. Starting to call Zephyr. Yeah, and a file fixer. Stage and formatters have their say. Unlock my, so I can sign it and push it. So if you want to follow along, you can go to my GitHub. GitHub TinyUSB CircuitPython. And then what I do, oh, well, it tells me Zephyr, but what I recommend is this branch button is actually really helpful because it tells you like the most recent branches and when they were updated. So if you want to follow along, there's that. Okay. Thank you everyone for joining me for this deep dive. I will not be deep diving. Tim may be, but I will not be until January because I fly to New York next week, and then you might see me on some other streams, but I'm not planning on deep diving. And then I will be in Michigan for the holidays until the new year. So I will be back in January streaming for a few months before I go on more paternity leave. If you want to join the Discord, you can go to the URL adafru.it/discord to join the Discord server. If you want to support me and Adafruit, you can go to adafruit.com, purchase hardware there. And I think that's it. Thank you to DCD for taking time codes. I already got the email. And thanks to Foamy Guy, as always, for covering for me when I'm out. So thank you, everybody. Have a great weekend and holidays, and I'll see you in the new year. I do plan on doing CircuitPython 2025, especially because all this stuff is very much what's going to happen in the future of CircuitPython. So think about things you want to do in CircuitPython in the future, and expect to see a blog post from me around the start of the new year asking folks to post their ideas about CircuitPython 25. Cool. Have a great weekend. I'll talk to you later. And I guess I should do window cam. It's dark. You can see my light reflections. It actually looks better than I thought it would. Sun is going down.